applied to various real-world problems. He has given more than 100 plenary lectures and conference tutorials in these areas. He has authored or co-authored over 1,300 plus publications with colleagues from nearly 40 countries. He has more than 37,000 plus Google Scholar citations with an H index of 91. Some of his research works have also won Best Paper Awards at 8-star international conferences. Dr. Abraham is a senior member of the IEEE, the IEEE Computer Society, the Institution of Engineering and Technology UK, and the Institution of Engineers Australia, etc. He serves or has served the editorial board of over 50 international journals. He is the founder of several IEEE-sponsored annual conferences, which now have become annual events. Some of them are Hybrid Intelligent Systems, which is 11 years old now, Intelligent System Design and Applications, which is also 11 years old, Information Assurance and Security, 7 years old now, Next Generation Web Services Practices, 7 years old, Computational Aspects of Social Networks, 3 years old, Soft Computing and Pattern Recognition, again 3 years old, and Nature and Biologically Inspired Computing, 3 years old. Besides a university professor, currently he is also the director of Machine Intelligence Research Labs, which has members from 100 plus countries. Since 2008, he is the chair of IEEE Systems Man and Cybernetics Society Technical Committee on Soft Computing and a distinguished speaker of IEEE Computer Society representing Europe. He has research expertise in machine intelligence, soft computing, neural networks, fuzzy systems, data mining, global optimization, and multi-agent systems, etc. His domain experience includes information security, web intelligence, web services, financial modeling, scheduling, etc. If you are interested, my friends, in knowing more about him, you have to visit the following web pages: www.softcomputing.net and www.mirlabs.org. So today, as you can see, he is with us and he is going to share his thoughts on Industry 4.0, role of data sciences and AI. With this, may I now request Dr. Raji to kindly address the audience. Please welcome, sir.
Very good morning to all of you. Am I audible to all?
Yes, yes sir. Yes.
Very good morning. Thank you so much for this opportunity to address this faculty development program, which is very timely during this crisis we are going through. And today I'm going to give you a quick walkthrough about a new academic jargon which is slowly getting popular all over the world. The title Industry 4.0 or the Fourth Industrial Revolution. It is actually a major topic. It covers almost all the major scientific areas from robotics, augmented realities, various manufacturing technologies, computational aspects from high performance computing, cloud, etc., to the data analytics part, big data, AI. So today I'm going to just focus on a very small part of Industry 4.0, just talking a bit about the role of artificial intelligence and big data analytics, what these things can do in Industry 4.0, the fourth industrial revolution. So all of us are going through one of the most difficult times in our life, I would say. Before, I would say I used to start my talk, Industry 4 has changed the way we live, but nowadays I usually start my talk telling about COVID-19, which has really changed almost everything from educational aspects to economics to basically almost anything we can imagine. But on one side, if you look at, from a positive side, especially for academics and those who are working in research, this is like a golden period to focus on some very good projects, publications, and you can turn this time to make this a valuable time to increase the productivity. Since I'm the editor-in-chief of a big journal in AI, I compare, the massive change. For example, last year, this time we used to get number of papers, and if you compare with the volume, there is almost like 50% surge in the volume of publications, which really means that people are spending more time for research and improving the productivity. So my kind request is to the academic community is try to see this as a positive opportunity, convert that to good research publications, etc., etc. So I always try to see things on a positive side, even though we know that there is no still light at the end of the tunnel. So my idea here is to actually give you a quick introduction. What is this huge topic about? And then since the topic is very big, I guess we will have to have more like interactive sessions. So once I finish the talk, we can actually have an interactive session where I will be able to answer more in-depth questions. Since I am sure that all of you are coming from various backgrounds, so my talk is also more generic. I'm not going deep into any major technologies, no equations, no mathematics, no algorithms, no codes. So basically anyone can follow my talk. So I will give you a quick introduction about Industry 4.0, then followed by data sciences and so-called AI or intelligent computing, what it can do in Industry 4.0. Then I will also present some of our own work in this area of computation intelligence or artificial intelligence, which we have developed during the last almost 20 years. Finally, some conclusions. So for those who are very new to the terminology, fourth industrial revolution. Actually, the first revolution dates back to the 18th century when we tried to use basic mechanical power. Basically from water and steam, we try to mechanize some very simple machines. For example, turning wheel. By using water, you can imagine you have some agricultural fields and transferring water from one field to another field. Basically very simple things like that. Slowly moving to steam. And in the beginning of 20th century, we have electric power available. So we were able to use massive electric generated power for various automation activities. It is also called as the second industrial revolution. 1970s, early 1970s, we had a lot of progress in some computational aspects, hardware, embedded devices, the birth of artificial intelligence. We were able to make a lot of automated products, slowly taking it to even to manufacturing level, which is called as the third industrial revolution. And the fourth industrial revolution, I would say during the last 10 years, we are seeing a big change in the entire dimension of manufacturing, where we are seeing the integration of so-called Internet of Things, cyber physical systems, artificial intelligence, big data technologies, augmented realities, various manufacturing technologies integrated with modern high-performance computing platforms, cloud, fog. securing this infrastructure, various security platforms. So altogether contributes to this niche area of Industry 4.0 or the fourth industrial revolution. So we are just experiencing the fruit of the so-called fourth industrial revolution, and actually it was during the time the COVID-19 actually changed the many aspects of our life, affecting the economy, various businesses, industries, manufacturing, etc., etc. I'm sure all of you are very familiar with the Internet of Things, where we have a network of various connected devices, sensors, measuring instruments, computational devices. So basically we can use such interconnected sensors for monitoring systems or for overseeing something or making some quick analysis of some situation. So basically the potential of such network devices are massive. So basically we can think about improved performance at a very reduced cost level. We can actually design innovative services. We can actually generate new revenue streams. And these are actually, I would say, at the very basic. And if you can transform this into the economics, the finances, I guess the benefits are really unimaginable. So these type of networks are already been in use for various applications. Basically, almost all defense organizations are using this type of technologies in manufacturing, even in commercial scale, even in, I would say, down to the society, even to street level. You can see these type of applications nowadays, the usage of Internet of Things, connected with, sometimes linked with cyber-physical systems, where we have a cyber physical interaction where we try to control something over the cyber infrastructure using a control system, or based on some decision sciences, we try to monitor some application or control something, etc., etc. So such environments are these days becoming very, very common. And when you have all this massive amount of data from these various devices, cyber-physical systems, all these manufacturing technologies, we need to really handle with what we call as the real big data. We're talking about petabytes, exabytes of data. And even this platform itself has evolved during the last 15 years because of the need for various analytics, basically from the business sectors. They want to find intelligence from the data, so they have tried to design various methodologies, and there came a huge area called as big data technology. And nowadays you can see conferences, journals, etc., focusing only on big data. So we have Hadoop, for example, is more like a kitchen to cook big data. So basically it provides a nice platform to understand the basics of big data, MapReduce, various other off-the-shelf platforms. Then you have, again, some open source platforms to have some deep insights of the data. For example, you have SPSS SAS, these are commercial packages. Then you have MATLAB and various other open source platforms, for example, like R, where you can use them for big data analytics. But the problem many a times is if you want to have a deep insight, if you want to know what is inside your data, for example, you have 1 million tweets, or you have an election campaign and you have a political organization or a political party trying to make a lot of tweets, and you want to find what this massive volume of tweet was all about, some sort of summarization or sentiment, what this millions of tweets talk about. So then we need some sort of deep insight, or we need to really come up with a more detailed methodologies. You need to probably do some understanding the data itself, from data cleaning, data processing, feature selection. They need to decide various methodologies. For example, if it is text, you need to decide some suitable text mining methodologies. If the data is stream, for example, if it is a stream of videos, then you need to do some analysis based on the data itself. So basically, you can see there are a lot of challenges when it comes to real massive volume of data, and especially when it comes from various environments. So big data technology itself, as I mentioned, there are a lot of challenges. For example, you have to deal with data which is coming at a very high speed, velocity. Sometimes you have variety, sometimes you might have to deal with videos, various multimedia formats, you have HTML, you have all this numerical, you have instruments. So basically, you deal with all these various types of data. So from a business intelligence point, or from an AI point of view, what we call is finding intelligence from the data is almost like finding patterns. So if I can find some pattern in a data, which that really means that we are able to find some intelligence. For example, if I have sales volume of a company, and if I can find some patterns of my customers buying products, which my competitor doesn't know, means I can design my manufacturing and sell those products in the best possible way. So that is called as business intelligence. So basically, finding those unknown patterns, that is actually what we are dealing with. We are trying to deal with AI. If you look at the sky, if you can say that, will it rain, which others cannot say, then definitely imagine a model. If you're a model like that will be very successful. So there are also different types of patterns. Some patterns are very structured. For example, you have iris, you have fingerprints, you have signatures, you have voice, you have face, you have gesture patterns, you have gait patterns, like how a person walks. So there are different types of patterns, and we can make use of these patterns and try to develop various methodologies. So for example, here you are seeing a list of number plates, a sample set of number plates from various states in the US. So if you look at these plates, they look like very similar. They have a pattern. You can see some state name, then you have like a 6-digit number for each state, and you can easily use some basic segmentation, extraction, recognition. You can easily use some very simple AI methods, and you can easily recognize the license plates. It's very easy. For example, if you have such a system in your home, or probably in a university, probably your barrier can automatically raise. Probably you don't have to press a button. So the barrier can raise automatically based on the arrival of a car. And imagine if you have thousands of cars, you can actually replace certain manpower, and probably this may be more efficient than humans, because this can work 24/7 without much efforts. So such simple systems are already in practice in various applications. So typically what you do in machine learning or artificial intelligence is we try to get some representation of the problem, or we try to get the data related to the problem. And then we try to build a model. So initially we try to train the model. And then once we train the model, we try to save the model. And then we test it using various test cases. So we try to train the model. Before that, we need to sometimes do some data cleaning. We need to make sure that data is very clean, doesn't have much noise. Sometimes we need to look into correlation aspects. They need to find the right features. Some features may not contribute to the results, so we need to find those right features. And then we try to use the model, train the model, we save the model, and then we use what is called as test data, which is not seen or used during the training phase. And then we see the results, how good the results are. Whether the test results are compatible with the training results. For example, if the test results are very high compared to the training result, which really means that the methodology is not working very well because it has not generalized. On the other hand, if the test results are very low compared to training results, it might depend. Probably we might have covered the entire domain or the problem domain too much, and algorithm is working very well. Or on the other hand, it could be also a problem with memorization. The methodology has memorized the entire domain, but if you show it, in a something different way, probably the method might not work very well. So we need to actually take a lot of care when we build the training model as well as when we test, and then we try to iterate or we try to fine-tune the performance. So many times we also need to find a good set of features. It is important to find which features contribute to the output. Sometimes there could be correlating features. Sometimes some features may be totally redundant, not causing much value. Sometimes some features may not be complete. Sometimes you could have invariant features. So sometimes you also deal with what is called as curse of dimensionality, especially when you have thousands of features. For example, like genome data where we have thousands of features, then we need to really design a method such that you try to get only the minimum number of features so that it can work in practice. Another problem which we often come across when you design a model is dealing with complexity. So sometimes you are able to build a model which works very, very easy and it gives very reasonable results. For example, if you want to classify two different types of objects, it is more like drawing a straight line, or y is equals mx plus c, or high school mathematics. But sometimes you cannot simply draw a line because the separation is not so easy. You might have to really build some models so that it can categorize them into two classes in the best possible way. So it is always favorable to use a model that is the least complex. So if you have two models and one is very simple and you have another model which is very complex, then it's always favorable to choose the simplest model so that you are able to explain the results, why you got the results or why you didn't get the good results or why it didn't perform, etc., etc. So the more complex the model is, you might find difficult to give proper reason for the performance, for the poor performance, etc., etc. There is actually a some nice theory behind this, how to select suitable models, etc. So for those who are new to this whole field, actually we can see the whole problem domain from three different perspectives. One is function approximation. For example, regression. Given today's, for example, I mean nowadays a very good problem which you are facing every day is the spread of COVID-19. So given the spread during the last 3 weeks, and based on today's number of cases, what will be the predicted number of cases for tomorrow and for the next 1 week? Simple regression model. Classification, whether we can categorize into two categories. For example, if you have a COVID patient's X-ray and a non-COVID patient's X-ray, and then if you compare them, whether we can categorize them into COVID patient and non-COVID patient. Lung X-ray, which is actually a very common way to detect COVID patients these days. Pattern recognition is another major area in AI where I've already shown you some examples, from number plate recognition to iris to various other patterns, understanding patterns. Clustering is another interesting area where we try to group or categorize similar looking objects. We try to group similar looking objects as close as possible, and those objects that are different as far as possible. It's a very nice methodology, very often using unsupervised learning methodologies, and it is very good for understanding data in a very fast way or at a very basic level. If you want to have a grip of what this data is all about, basically I would say the best way is to do some clustering and see how your data looks like, and then you can build models based on that. Approximate reasoning is another methodology, or very important methodology, where we try to build in approximate reasoning methods. In real world, many a times, if you go for precise, exact solutions, it might not work. And many a times we need to solve a problem, and many a times we can solve those problems with so-called near exact solutions. Of course, we are happy if we have the exact solution, but if it takes 1 hour to compute what is the exact solution, then it might not have any value. So basically, our idea is to design methodologies that can handle imprecision, uncertainty, vagueness, etc., which is very common in our daily life. Another big area is the field of optimization, where we try to find the best solution from a given set of solutions, or in some cases we even don't know what is the exact solution. For example, if our task is to find what is the best shape of a pen, I guess it is very difficult even for us to say what is the best shape of a pen, because we are seeing a pen since when we are small kids, and now we are grown up, and now some of us are very old, and we still believe that this is a pen and the shape is like this. But is this the best shape, or is it, whether this is the optimal shape, whether it is the looks, aesthetics, the cost factor, the life. So a lot of various, I would say, constraints, objectives are involved when you design so-called, if you want to find an optimal solution. And many a time we humans, we don't know what is the best solution for a particular problem. So the idea is to use machines or AI to find the best possible solutions. Of course, if you can find the best or the optimal solution, of course, it is better, but at least if you can get to near optimal solutions, and if you can solve a particular problem, then we are able to achieve something. So that is the basic idea of optimization. So in a nutshell, we can say that the main components are approximate reasoning, which I just illustrated. And you can think about various probabilistic models based on historical data. For example, if we can easily put rules like, for example, if there is cloud in the north direction and if there is cold wind coming from this direction, there is a probability that it might rain. Right? It is more like, we simply found this based on experience. So probability is a very useful tool, especially for very, very small problems or solving very, very practical situations. Fuzzy logic, rough set, used to model uncertainty, tolerance, fault tolerance, imprecision, vagueness, etc. Neural networks is very, and those sort of methodologies are highly used for function approximation, regression, classification, pattern recognition. Evolutionary algorithms are a class of algorithms used to find optimal solutions. If you want to find optimal solutions, we can use evolutionary methods. So basically, you can see with these blocks, we can actually solve a wide range of problems faced in various applications. So optimization, like I mentioned earlier, is more like a fundamental tool for finding the best solutions for a given problem, whether it is finding the best shape of a valve, or whether you want to design the shape of an aeroplane wing, whether you want to design the shape of a car, whether you want to find the best shape of a pen, or whether you want to tune some parameters of a controller. So basically, all these are done using the so-called global optimization algorithms. And recently, a modern trend is to use what is called as meta-heuristics, where we try to borrow ideas from nature, or we call as nature-inspired meta-heuristics. So Mother Nature has a very nice way for solving practical problems. So the same way we try to mimic what is happening in nature to mimic and use those methodologies for solving some of our practical problems. For example, if you look at the sky, you can see a group of migratory birds. They might be coming from some other parts of the world, traversing various forests, states, countries, and even going to another continent. And after some time, they return back to their homeland. So they basically follow some trajectory. And if you look at these groups, there are no distinctive leaders. Basically, there is a flock, and they have some intersocial communication and some sort of indirect information exchange. So basically they all follow together some way, and then they try to manage and traverse, for example, they traverse all the way from Siberia to India, for example, a good example. Imagine the amount of distance and the various challenges they might be facing along the route. So you can imagine if you can implement that, a group of robots, and they are trying to go to a street on fire, or a building on fire. So imagine if they can communicate each other, and if they can rescue those valuable goods, or if they can rescue people in danger or assist firefighters, just to give you an example. So these type of models are being used in solving several practical applications. So the entire field comes in the umbrella of meta-heuristic, and evolution algorithm is sort of one popular algorithm which is based on Darwin's theory of natural selection, where the idea is fitter the parents are, they will get opportunity to find food, and they will produce the best offsprings. Usually offsprings are better than the parents. And we try to mimic this in a artificial way, where we try to have a potential solutions to a particular problem, and then we try to use some operators like crossover mutation to change these solutions, get the next generation, and we keep on doing this until we get the next generation of solutions, and repeat this process until we get the so-called optimal, or sort of the best solution which satisfies our need, or it could solve some practical problem. So one popular method in the field of machine learning, or AI, is the field of artificial neural networks. Almost close to 70 years old, since we had the first neuron and the perceptron learning rule, giving rise to multi-layered perceptron. Then we had the backpropagation, etc., and several other complicated learning methods. So the basic idea is to mimic the mammalian way of learning from examples. So we humans, for example, we can learn from examples, and we can also generalize. Over time, we are able to understand the problem domain very well, and we can actually make wonderful decisions. So we are trying to mimic this in a very artificial way, and we call it as artificial neural network. Like I mentioned, there are probably more than 100 different types of networks and learning methods. And the recent trend is to use what is called as deep learning methods to improve the performance of traditional neural network learning methods. So basically what we do is we try to present a set of features, and then we try to get what is called as a class. So for example, we want to categorize them into two classes. So we have inputs, outputs, and the idea is present these inputs, and then you make the network learn such that it produces the correct class. Okay, so for example, in this problem, you are seeing 3 features and 2 classes. So you present the first feature. Once we initialize the network with some random weights, we present the first feature, and then it is propagated in a forward direction because it is a feed-forward network, and you're getting an error at the output, and then depending upon the error, you need to adjust the weights so that you again try to produce the correct or required output. So the basic idea is you force the network to learn the correct weights so that given input, you also get the correct output. So given these features, idea is given the features 1.4, 2.7, 1.9 should get a class value 0. So until we get the class value 0, we try to present these examples such that the network produces the correct output. Similarly, you present another input feature and then you pass the data through the network and then you get an error and then you see you again need to adjust the weights. And you have to keep on doing this probably thousands or even millions of times depending upon the complexity of your problem. So basically, this is how it looks like from a decision boundary perspective. So basically, if you have initial random weights and you have the initial decision boundary, you could see that it is spread between the two classes. And over time, as you adjust the weights, you could see that slowly it is able to draw that beautiful line between the two categories. So this is all about learning or how to approximate the given input output, function approximation. So from a decision boundary perspective, if you have very small neurons, for example, here you have like 3 cases where you have 3 hidden neurons, 6 neurons, 20 hidden neurons. So if you have 3 hidden neurons, you could see that the decision boundary is sort of very, very, very simple. If you have 6, you could see that decision boundary is a bit more complex. And if you have 20, you could see on the extreme right, it looks more complicated. So by adding more neurons, sometimes you are able to make a very complex decision boundary. Okay, less is more. You might not be able to categorize complex data, but when you have more hidden neurons, you might be able to categorize them more accurately. And the problem starts getting complicated when you have a lot of features. For example, if you want to design a network that could generalize handwritten digits from 0 to 9, and if you look at the various features, if you transform that into a matrix form, and then imagine if you have this matrix in the form of a binary string 0, 1, 0 when you don't have something inside, and 1 when you have something inside. 0, 1 if you just put it in a matrix form, and if you just make it in the form of a neural network learning procedure. And I just want to give you a quick introduction to deep learning, what deep learning does in this case. So there are several hidden layers which tries to learn what is called as high-level features. For example, we humans, we can understand people or understand objects or understand even problems based on high-level features. For example, if I see someone walking, even if I see the person from a side, I could still understand that it is him or her. So I have some understanding of some high-level features. Similarly, if you see an object, probably you don't have to see the whole object, but just a small fraction of the object, you can still make out that it is that object. So we are able to understand high-level features, and a very similar idea, we are trying to mimic this using what is called as several layers. So there are some neurons which are focusing on certain aspects of the input. For example, some neurons may be learning only those horizontal lines. Some neurons may be learning only those which has dark area in the top left corner, because this is a hand-written digital number. So basically, some neurons are focusing on some areas. Some neurons are focusing on vertical lines, some are focusing on horizontal lines, some are focusing on small circles, and how it is positioned within the digit. And if you put them together, high-level features, if they put them together, then basically what you're getting is a beautiful neural network trained using deep learning method. So basically we try to train the first layer, then it is transformed to second layer, third layer, and finally the output is presented to the final layer. So it's a very simple method, and each of these layers is trained to be an autoencoder. So basically what it means is it tries to learn high-level features from the previous layer. So basically it is forced to learn high-level features from the previous layer. So there are several ways for designing networks. So I was talking about multi-layered perceptron to deep learning, and one very popular area is the field of evolutionary neural networks, where we try to use evolutionary or genetic algorithms for designing neural networks. For example, if you have a network on the left and right, so the idea is to have a network which is smaller in size and faster convergence, and also has better generalization. So imagine if you have a network, feed-forward network, like when you see on the right side, feed-forward network. So basically you can map that in the form of a matrix. So where you only have the lower half because there are no upper half, because there is no feed backward connections. And if you put them together in the form of a chromosome, which you see on the bottom part of the slide, if you have a chromosome, and you can use simple genetic operators. For example, like you have crossover, you have two parents, two neural networks, and then you have a totally new neural network, a new baby network. So basically it is different from the parents and supposed to be better than the parents based on Darwin's theory of natural selection. You can actually change the network by using mutation, for example. So mutation is a very, very interesting method where we try to change some parts of the network. For example, when you see on the left side is original network, and just by changing some values, you get a totally new network with a totally different set of weights. So there are several ways, like I mentioned earlier, and one method which we focused on was using the concept of flexible neural trees, where we try to provide only predefined instruction operator sets, and then we try to have what is called as a flexible tree model. So basically this model can do feature selection, and it can actually use different activation functions at different nodes, and basically it is able to design the entire network using some automated method. So basically it is a version of genetic programming where we try to use tree representation for designing such networks. So basically, if you give what is called as an instruction set, for example, +2, +3, +4, +5, and then you have the terminal set x1, x2, x3, what it really means is the instruction set +2 means it can take 2 instructions, +2. So basically, it can select variables from x1 to x3. Similarly, we can have like instruction +6 means it can take 6 instructions, and it can take. So you can imagine just by changing the instruction set or the value of the instruction, you can actually explore the search space more efficiently in a much faster scale. So that is the basic idea of using flexible trees. So I'll skip some of the details because you can easily find them from some papers. So basically, I just want to give you some samples from some of our results. For example, here you have two cases where we have one with a lower number of features. For example, case one is with two inputs. So basically, this is for the gas furnace time series. There you have two inputs and one output. So for two input, one output, this is actually the error which you see here, FNT model case one. And we try to inject what is called as time lags. When you try to inject time lags, we are able to minimize the error by almost half. So by injecting 12 time lags to each input, we are able to reduce the number of the error values to almost half. This is for the Mackie glass time series. We have 4 inputs, 1 output. Again, if you look at the last 2 rows, case 1 is without time lags, case 2 is with time lags. And with time lags, you could see that the error value has gone down by almost half. So basically what I want to tell here is by having time lag, sometimes it can also help to improve the performance. Intrusion detection is another popular benchmark. So yeah, it has 41 features, and in many cases you just need only like 8 to 10 features depending upon the classes, and you can get almost like 99.19, 98.39. You can see the accuracy spreads in various ranges. Okay. Colon cancer, leukemia, these are all, I could say, benchmark data sets. Again, comparison with various other machine learning models. The flexible trees, you could see that it's 97.09% compared to other models. Colon cancer data set, 99.6. You could see the error for various other models. So one issue which we came across when we designed such network is the problem with, or how to decide which network is the best. For example, we have a population of solutions, and we have a network which is small but the error is very high, or we have a network which the error is very low but the complexity is very, very high. So sometimes we need to have a trade-off between complexity and accuracy. And many times we also found that, or people working in this field, they know that if you have a diversity of activation functions, then that also helps to improve the performance. So we try to formulate diversity of activation functions, the complexity and accuracy as different objectives, or what we call as a multi-objective problem, and then we try to project them what we call as a Pareto friend, where we try to make a trade-off, or we try to find what is called as Pareto optimal solutions. So we try to use Pareto optimal designed flexible trees, and we try to use for various problems. These are some classification benchmarks, some benchmark data sets. So you could see that some of them requires only very less features, and the accuracy is sort of very reasonable. This is the wine data set. It has like, I think 30 plus features, and you could see that it needs only 5 features and very compact network. So such a compact network, you can actually model the wine data set. We also use the model for regression. These are some regression benchmarks, 5 benchmarks. You could see the train test models. There are different models. So that was like the one aspect of machine learning, where we try to use function approximation. I illustrated various models, and the last part, I would say, for the next 5-10 minutes, I'll be able to finish this lecture. So it's on designing expert systems. where we try to use very similar models to design expert systems. I'm sure all of you are very familiar with fuzzy logic. If all of you are not familiar, I'm sure that all of you are users of fuzzy logic. If you have a modern camera or a washing machine, you might be having a fuzzy controller inside. So what you see on the screen on the top right corner is actually a fuzzy rice cooker. So based on the volume of rice you put, regardless of what quality, and you pour some water, and depending upon the water and the rice quality, the machine will automatically decide how much time your machine needs to cook the rice so that it meets your requirement or it meets your standards. So fuzzy logic is based on the concept of fuzzy sets, fuzzy if-then rules. So if you use Boolean logic, for example, if you want to define a set of old people, for example, if you say a person who is 80 years old, you would say that he is 1. If he's 80 and 79.99, we would say he's 0 or young, which is not correct. But if you use fuzzy logic, we use the concept of membership function. We say that if someone who is 75, he has a degree of association of 0.9. And someone who is 65, he has a degree of association of 0.5. Or we say that he is 50% old or he is 90% old. Okay, so using such simple methods, we can actually build uncertainty, imprecision, and vagueness into traditional crisp if-then rules and also to traditional expert systems. So if pressure is high, then volume is small. So where we have pressure and volume are fuzzy values, fuzzy variables, and both are fuzzy sets. And there are various types of inference methods. And basically anyone who wants to know about this, you can actually simply search literature and you can find tons of tutorial materials, textbooks, reference books. So I'm not going into detail. So basically, once we want to design expert system, you need to decide the relevant input-output variables, which fuzzy inference method you would use, the number of linguistic terms we would use for each variable, how we will decide or how you will design these rules. And if you go one step down, you need to decide the number of membership functions per input variable, how you will build the role, the knowledge base, finally fine-tuning the membership function parameters and various other parameters. So one popular method is to use what is called as neurofuzzy methods, where we try to use neural network type learning methods to learn fuzzy expert systems. So where we try to establish an expert system in the form of a network, and then we try to use conventional backpropagation method or another approximation method to learn the various parameters in that expert system. Again, this is a very established research field, I guess almost 30 years old. So I just want to give you a flavor of what neurofuzzy systems could do. For example, this is for the Mackey glass time series. So if you look at the y-axis, the bottom one is the neurofuzzy inference system. And if you compare the neural network, you could see that error is almost 1/3. Okay, a neurofuzzy system produces 1/3 error compared to an artificial neural network trained using backpropagation algorithm. So there is neurofuzzy. There is also another design method called evolutionary fuzzy systems, where we try to use evolutionary procedures to learn fuzzy expert systems. One such approach is called Michigan approach, where every chromosome forms a rule. So the entire population becomes the various rules of an expert system. And then you can imagine your operators, various genetic operators, mutation crossover, you're trying to evolve a single rule base. In a Pittsburgh approach, every chromosome represents an expert system itself. So you can imagine a population of expert systems. So mutation and crossover creates entirely new sets of expert systems, very different from Michigan approach. In the case of iterative rule learning, we try to start with a small rule base, for example, like Michigan approach, and then we try to add new rules depending upon the requirement of the output. And sometimes we prune the rules, or we try to delete those rules which are not contributing. We try to adapt and learn depending upon the output requirement. Okay, so all these are, I would say, very popular learning method. So just to give you a flavor, you want to compare with a neural network and a evolutionary fuzzy system. You could see that neural network is on the bottom, 0.0047, and an evolutionary fuzzy system, you could see that error is 0.0008. You could see the difference. So even compared to a neuro fuzzy system, ANFIS, you can see the error is 0.0017. So for evolutionary fuzzy system, the error is almost half. So you're able to optimize the rule base and the parameters to such a level that you're almost getting what is called as global optimal solution. So we try to use a very similar approach, like the flexible tree approach, for designing an expert system. So where we try to break the rule bases into small rule bases, and somehow we try to interconnect them, and we try to make this design procedure very similar to the flexible neural tree approach. And for those who work in fuzzy expert system, we know that once we go above some number of input variables, we have the problem of curse of dimensionality. We cannot really understand the performance of the system because of various issues. So somehow we need to minimize the number of features to design a fuzzy expert system in such case. So the idea is to break down these rule bases into small rule bases and somehow try to interconnect them. So imagine if you have 4 input variables, x1, x2, x3, x4. So you can imagine you can break the rule base like this, or like B on the top right, or C bottom left, and D bottom right. And imagine if you have x1 to x100, or x1 to x1000, 1000 variables, and imagine the various ways of interconnecting them. So it brings a very big challenge to design such an optimal model. So basically we try to use a very similar model like I mentioned earlier, the flexible approach where we just need to press an instruction set, +2, +3, and the variables x1, x2, x3, x4, and then the algorithm automatically constructs what is called as trees, which is mapped to so-called expert systems. So I will skip some of these basic results. So this is what iris data. So basically it has 4 features. So during 10 runs, you could see that sometimes it requires only three features. So here if you see that the third run, you could see that it needs 3 features and almost 100% accuracy. And here also we have this very similar problem. We have a smaller tree, which is sort of very compact, but probably error is very high, or a bigger tree, which is more complex, but error is very low. For the wine data, it has 13 plus features. So sometimes you see it requires only 5 features and accuracy is almost 100%. Sometimes it requires only 4, 99.4%. So you could see that, again, a trade-off, a smaller model or a bigger model. A small model which is very, very compact, or a bigger model which is very complex. So we need to have a trade-off between what is called as complexity and accuracy. A very similar case like I illustrated earlier. So we need to have a trade-off, and then we try to use a very similar approach where we try to use a multi-objective design method. And this is actually for a controller. And we also try to explore type 1 and type 2 for these systems. So for single objective type 1, you could see the errors like this. Multi-objective type 1 errors like this. So you could see that when you shifted from single to multi-objective, you could see that error is reduced. And when you switch to type 1 to type 2, you could see the error has again gone down. So if you look at type 1 single objective to type 2 multi-objective, you can see the error is like reduced from 0.0043 to 0.0028. Error has gone down so much. Another example, control system, you could see again type 1, type 2, type 1 on the bottom, type 1 on top, type 2 on the bottom, single multi. So you could see that here, not much difference, but if you look at multi-objective type 2 fuzzy, you could see the error is reduced. Okay. A very interesting application where we had like almost like 300 features. So if you have 300 features, designing a fuzzy expert system is sort of out of question, because even if you have two fuzzy sets per input variable, you can imagine 2 raised to 300 rules. So many number of rules, because of dimensionality. So we have to find suitable ways to reduce the number of features. So we try to use the hierarchical method, and you could see that type 1 multi, type 2 multi. So you could see the type 2 multi, you could see the error is reduced to 15.25, and it requires only 4 input variables. So from 300 features, we were able to reduce to 4 features, okay, which is like a very big achievement. So to conclude, I guess Industry 4 provides us a very nice framework to have a nice convergence between cyberspace and physical space. Will enable AI on big data and robots more effective. We are going to see a lot of interplay between various technologies. We're going to see from mass production to things moving to mass customization. There are a lot of challenges. For example, we need to design methods which are fast, produce very good error rate, computationally inexpensive. And many times we also need to decide methodologies which could also understand the data in a much better way. And for many data analytics, data mining problems, the more time you spend to understand the data, you might be able to build a better model and also produce better results. I guess some of the issues I already mentioned earlier. We need a very good data processing. We need a very good representation of the problem itself. Okay, only then we can actually build a very good model. Otherwise, finally, we will have to say that this model doesn't work, or AI or machine learning doesn't work for these type of applications or these type of problems. So basically, the root cause is we are not able to understand the problem itself in depth. So the more time we spend to understand the problem and to understand the basics of the data, then we will be able to build a better model. So thank you so much for listening to me, and now I am open for questions.
Thank you so much, sir. Thank you, first of all, for such a nice presentation. You can see there are a number of messages in the chat section for the appreciation. So you were able to cover so many topics with such a great ease that it was very easy to follow the presentation by the participants. So as you said that you are open for a question answer session now. So what I'll do, I will read one by one all the questions in the section. Let's see how many questions we are able to take. first question is this possible to optimize the weight and apply it to neural?
I didn't hear the question very well. Is it possible to optimize the weight?
Yeah, is this possible to optimize the weight and apply it to neural network?
Sorry, the last part is not clear. It's possible to optimize the weight
And we can apply it to neural network. Means the modified weights can be applied to neural network. However, as far as I know, it is possible, but I would like to hear the expert comment.
Yeah, definitely. So basically, there are so many different methods to find best combinations of weights. So basically, training or learning in a network, basically we are trying to change the weights. We are trying to find the best combination of weights, whether it's backpropagation, whether it's deep learning, whether it is evolutionary network, whether it is flexible trees. Basically, all we are trying to find is finding those magic numbers. So basically, it is a NP complete problem where we are trying to find what is called as near optimal solutions to solve that particular application or the particular problem. So basically, all we are doing is adjusting the weights and try to find the best possible answers. So that's about it.
Well, yeah. Another question is how we can optimize the output by integrating fuzzy logic with uncertainty modeling.
Well, this again links back to my second part of the lecture where I talked about expert systems. We basically fuzzy expert systems deals with uncertainty. So basically, all your inputs are translated to fuzzy variables. So each variable could take all sorts of uncertainty. For example, if you say if you want to model age is a variable, and like I mentioned, like if you ask someone, how old are you, you will say, I'm not very old, or more young, not old. People use different words, but we can actually translate all this uncertainty and imprecise, vague ideas so that a machine can understand. So fuzzy logic or fuzzy expert system is a very nice framework to model uncertainty and optimization. And once you have this basic rules and variable set, then you can optimize them using various methods. Like again, I mentioned earlier, neuro-fuzzy systems. You can use evolutionary fuzzy systems. You could use flexible trees. So there are various ways for integrating such uncertainty and also find the best values.
Yeah, thank you, sir. One of our participants is interested in knowing the difference between infrequent data, outlier data, and anomaly data. Some real examples.
So sorry, I forgot. I didn't hear the first one. Outlier and
infrequent, outlier, and anomaly data. Difference amongst these with some real examples.
Infrequent data, that is something like probably it is something very different from the other two, outlier or the other one you mentioned. Infrequent just means that it happens only one. For example, like solar eclipse, we know that it comes only once in a time, but it is well defined and well structured, and we know what it is. Outlier is something very different. Outlier is something which is entirely different from what is known. For example, if you find a flower with some very colorful petals, different from other similar flowers, that is more like an outlier. And anomaly and outlier, I would say they are very similar. They could be used many a times interchangeable. It depends upon the context. Anomaly, like the word itself means, it is usually by security experts. So people working in information assurance security, they try to find, like categorize things which doesn't happen very often, like zero day attacks, which is sort of, uh, totally, which is totally cannot be understandable by using, any the type of features or any machine learning methods. So anomaly is something like that. So basically, there are some similarities at the same time. These are used by different communities. So, for example, someone in the data mining or data science or AI would use outlier instead of anomaly, and someone from security field, they would use anomaly more than outlier. And infrequent is something very, like I mentioned, it is sort of like very structured and well known. So basically, it cannot be considered as an anomaly or an outlier.
Another question is from our very sincere participant, Mr. Vivek Tomar. He is interested in knowing, is there any simple method to decide which machine learning model would be good for a particular kind of problem?
Well, that's a very very interesting question, but I guess I don't have a good answer for that. Basically, I would say it is very difficult to find a universal problem solver. So we need to understand the problem in depth. We need to understand what the data is all about, and then we need to build a model, and then we need to understand why I need this model. Whether I need a model which should be interpretable. For example, if you have a model that is used for controlling a valve in a nuclear reactor, and you need answers. For example, if the valve is open, given some conditions, there you cannot use a neural network. There you need probably an expert system because you need explanations. Because you need to know why this valve was opened given this condition. So you need an answer for that. So you cannot use a black box. So sometimes you need what is called as interpretable model. Sometimes you don't care for interpretability, but you need accuracy. For example, like prediction of stock markets. Nobody wants to, nobody wants to know what will be the value of stock market, but people only want to know whether it will increase or decrease tomorrow. So based on that, I can invest money. So if you want to use very, very, those sort of models, depending upon the application, then you can make better decisions which model you should pick for a particular application. So again, I would say there is no universal problem solver. So I have introduced you different models using different methods. And I myself, I would say that all these models you can use for solving all the problems. Sometimes you might have to use an entirely different model depending upon the problem or the application.
Hope that answers the question of Mr. Vivek. Now, we have another question from Mr. Ankur Chaurasia. He is interested in knowing how to optimize the output by integrating fuzzy logic with, I think this is a repeated question. Yeah, I have already taken this question. We have already answered this question, sir. How to optimize the output by integrating fuzzy logic uncertainty model.
Yeah, I guess, yeah, we already answered that. I guess that was the second.
Yeah. So another question is, sir, what are the research trends in medical machine learning?
Well, I guess it's a massive domain. Actually, it's a massive domain, and understanding medical data sets also offers a lot of challenges. For example, privacy, security, a lot of allied issues. We can use most of the traditional machine learning models for understanding very simple medical problems. For example, like understanding a mammogram or understanding a CT scan or categorizing X-rays, for example, like I mentioned earlier, a COVID patient or a non-COVID patient, chest X-rays, or whether we can predict epidemics, pandemics, etc. Like you have seen different models being used. So actually, I would say there are a lot of opportunities for machine learning in medical domain. At the same time, we also need to take care of issues related to privacy, security, and various ethical issues. So we might have to use uh, machine learning models that are also able to understand these domains. For example, there is a very interesting area within data mining, which is called as privacy preserved data mining. So where we won't be able to understand which patient's data is this, or this X-ray belongs to which person, etc. So basically, it is anonymized